Welcome to the deep dive. So imagine this. You ask an AI to tackle a really complex new machine learning problem. How do you stop it from just, spitting out the same old answers it learned ages ago?
All right, the familiar stuff.
Exactly. And that's the problem MLE-STAR is built to solve. It stands for Machine Learning Engineering Agent via Search and Targeted Refinement. Today we're digging into how this framework gets around some major weaknesses in older LLM-based agents, like their reliance on static internal knowledge, and how they try to fix whole scripts at once, which is just clumsy.
Yeah, and that internal knowledge bias is a real technical hurdle. You see agents like, say, AID defaulting to things like scikit-learn or maybe ResNet for images.
Because that's what the base LLM knows well.
Precisely. They're often biased towards those familiar, maybe even outdated methods. They just don't have that deep iterative search capability you really need for tricky stuff like advanced feature engineering you see in competitions.
Okay, so let's unpack MLE-STAR's approach. First up is the search component. How does that tackle the bias?
Well, it's not just a simple Google search. It's more systematic. The agent actively searches external sources for effective current models.
So it finds descriptions and actual code snippets, like
Right.
blueprints.
Exactly, blueprints, yeah. So instead of just suggesting ResNet again, it might pull up, say, EfficientNet or even a vision transformer based on what's actually state-of-the-art for that specific problem.
Yeah.
It aims for better performance right from the start.
Got it. Better starting point. But you mentioned refinement being key.
Yes, the targeted refinement. This is where it gets really interesting, I think. It's data-driven. There's this outer loop where the agent essentially diagnoses its own code.
How does it do that?
It performs an ablation study on itself.
Wait, the agent runs an ablation study? Seriously? To find the bottleneck?
Yep. It experiments on its own generated script to pinpoint exactly which block of code is having the biggest impact on performance, positive or negative. No guesswork.
Okay, that's clever. So it identifies the critical bit.
Mm.
Then what?
Then an inner loop kicks in. This loop focuses only on that specific isolated code block. Could be feature engineering, maybe data transformation, whatever is critical. And it tries out, say, K different refinement plans just for that part. Crucially, it learns from each attempt.
So failures become feedback.
Exactly. It uses the results, good or bad, to propose smarter strategies for that component next time, before iterating back to the outer loop to find the next most critical block. It's very focused.
That sounds powerful, but also potentially risky if the agent makes a subtle mistake. Which brings us to those robustness modules you mentioned.
Right. Absolutely necessary. You've got the data leakage checker and the data usage checker.
Why are they so important?
Well, the leakage checker catches these really nasty LLM errors. Like, imagine the agent imputes missing values, but it uses stats from the test set to do it.
Ooh, yeah, that's classic leakage. Your validation score looks great.
Looks amazing. But then it bombs on the actual unseen test data because it cheated, essentially. This checker prevents that.
And the data usage checker.
That one makes sure the agent actually uses all of the relevant data provided. Sometimes you get these specialized data sets like geometry files, and if the agent ignores them,
Performance stinks.
right. Table 6 in the paper really shows how much difference using all the data makes. These checks are vital for reliable, high-quality output.
Okay, the proof is in the pudding. Let's talk results. MLE Bench Lite, the Kaggle competitions.
Yeah, the results are pretty striking. MLE-STAR medaled in 64% of the competitions.
64%, that sounds really high compared to the baseline. What was 8 again?
AID was sitting at 25.8%. So
Yeah.
yeah, a massive improvement. And get this, 36% of MLE-STAR's results were gold medals.
Wow. 36% gold. What drove that level of performance?
A lot of it comes down to a smarter way of doing ensembles. It's not just picking the best single run or averaging a few top ones.
How does it do it then?
The agent itself proposes and then iteratively refines the actual strategy for combining multiple good solutions. It figures out the optimal way to blend them.
So the agent optimizes the ensembling process too.
Exactly. And that agent-driven approach consistently outperforms simpler methods like best of n or just averaging, as shown in Table 4. It squeezes out extra performance.
So if we were to boil it down, the big takeaway for you listening is that MLE-STAR seems like a real step change. It's merging that external up-to-date knowledge with this very targeted, data-driven code improvement, all guided by its own ablation studies.
It really turns the LLM from just a generator into more of a targeted reasoner and optimizer.
Makes sense.
And here's something to think about. The paper shows MLE-STAR gets significantly better just by swapping the underlying LLM, going from Gemini 2.0 Flash to 2.5 Pro boosted performance noticeably.
Right, better reasoning leads to better results within the same framework.
Exactly. So the provocative thought is, as these foundational LLMs keep getting smarter, how quickly will frameworks like MLE-STAR start to genuinely challenge, maybe even replace, the traditional, very human-heavy way we do machine learning development today?
A big question indeed, something for us all to watch closely.